welcome to class, everybody, on this very rainy day. Okay, so before we get started with our content this week, I will introduce an activity that you guys can do. This is not mandatory, but this is something, the first week of class, we talked about why are you here? Like, what is your purpose for being here? Ideally, something more than just I'm required to be here, but there are reasons for why the department requires you to be here. So I want you to kind of think a bit more about this. So throughout the semester, I'm going to be giving you guys some prompts to think about to help you just to appreciate why you're here and hopefully help keep you interested and motivated to keep coming here because you understand the importance of what you're learning and you're able to apply what you learn to other areas of your life, not just for passing this class, but for other ways in which you might apply this kind of information. So on the discussion form, sorry, not on the discussion, under the assignments on Canvas, I have an assignment called Stats Matters. Many of you guys did the week 1 activity. This is the next one within the series of Stats Matters. So the idea is to help you guys to think about why is statistics important, not just for here in this class, but other classes you might be taking. So what other classes within your major do you think that you'll take? And then how can you apply the information that you're learning here to help you in these other classes? So there's a table there in the assignments. Just go through and just kind of check off what ways do you think that you might be applying some of the information you're learning here to other classes, and then just write a short paragraph about this. So if you wanted to do this, you can get 1 extra bonus point on your final exam. But again, it's not mandatory, but this is, again, just a way for you guys to think about how can you apply what you learned here beyond just this particular class. The idea being thinking about the relevance of statistics beyond 2132. Okay, so let's go ahead and begin with today's lecture. So we have 2 topics we're going to be covering today, reliability and different ways in which we might establish control techniques. Reliability really follows on what we discussed last week, which was validity. And oftentimes validity and reliability get put together because they are in fact very related. There's so much with validity. I didn't want to cram reliability in last week's lecture as well. So this is kind of a follow along to what we discussed last week. Okay, so let's go ahead and start. I have a question for you guys. What does it mean if a statistic has an associated p-value of less than 0.05? Okay, I'll give you guys a few more minutes to write in an answer. Okay, so let's see what we have. All right, this is always so hard to see from here, so let's... All right, this is a bit easier to see. Okay, so what do we have? Well, we have a lot of people talking about statistical significance. Yes, that's good. You guys have learned that statistical significance is related to this 0.05 criterion. So yes, that's correct. There's a high probability that the data did not occur by chance alone. Yes, that is a good answer here. Probability of getting that statistic if the null hypothesis is true is less than 5%, which means that the result is statistically significant and not by chance. Yes, very good. Good. So I'm getting a lot of people who are kind of have basically the good textbook definition, right? 0.05 or less means that the result is statistically significant. It's unlikely to have occurred by chance alone if the null hypothesis is true. The result is significant. Yes, that you guys know good that the p-value is associated with the confidence interval. The confidence interval we determine, so that 95% confidence interval is determined by that alpha criterion, which is the p-value. So good. Have a significant difference and possibly not occur by chance. Yes, can reject the null. Yes, good. So we know that when you have a statistically significant result, that means you can most likely reject your null hypothesis. It's unlikely that these 2 populations or these 2 groups come from the same population. Good. That is not normal. This is not quite correct. So it's not that it's not normal. It's more that it follows within the tail of the distribution. And so far, the result, your experimental group is so far in the tail of that distribution, of a normal distributed distribution, that it's unlikely to occur. It occurs with such low probability that it's just unlikely to have occurred by chance alone. So it's not that something is not normal. Oops, missed it. It's not that it's not normal, but it's more that it just follows within the very end of the distribution of a normal distribution. Good. So a lot of these are very similar. Of being a type 1 error, yes, that's correct. You guys, we learned in week 1 Again, that the type 1, type 2 errors are related to the probability of making that inferential error. So if you reject the null when you should have retained it, that's a type 1 error. And that is determined in part by your p-value. So where you set your alpha criterion to determine statistical significance is going to influence the likelihood of making these type 1 or type 2 errors. Okay, good guys. I'm seeing a lot of really good answers here. So let's, okay. So the reason I asked you guys to think about the what it means when something is less than 0.05, it means all those things that you guys discussed. That's great. I want you guys to think beyond just the textbook definition. When something occurs with a very low probability, what we're saying is that, yes, it's unlikely to have occurred by chance alone. Therefore, we're likely to get the same result if we repeat the experiment with the same population. That's the implicit conclusion, is that you should be able to replicate this result because it's not by chance, right? It's by design. There really is a difference between these two groups, or there really is a relationship between these two variables. And so if you go out and you sample a new group of participants, you should be able to replicate the same effects. That's what a p-value of 0.05 or less means. That's what we mean when we say something is statistically significant, is that it's likely to be real in the population, therefore it's likely to be replicated. So p-value is all about replication, or the reliability of the result. Reliability is all about, can we get the same results across multiple trials or across multiple participants? So when we talk about an experimental result having a p-value of less than 0.05, what we're really saying is we should be able to replicate this, that somebody else in a different lab or with a different sample, again, coming from the same population, it only makes sense if it's from the same population, but they should be able to replicate this result. So that's really what we're talking about when we say p-value of less than 0.05, is that this result is reliable. We can get it again, right? If something is not reliable, if something has a p-value of more than 0.05, it means we're unlikely to get it again because this result is by chance alone. So it's not likely that you're going to be able to replicate that result. So again, just kind of thinking about this idea of reliability and replication, that's really what the p-value is all about. Okay, any questions so far? Okay, so today that brings us into our first part of discussion, which is all about reliability. As I just mentioned, reliability is the ability to replicate a particular outcome. And there are different types of reliability that we are concerned with depending on the kind of design that you have, the research design. So we'll go through these four: test, retest reliability, alternate forms reliability, internal reliability, and inter-rater reliability. All right, test, retest is the easiest one probably. It's exactly as the name sounds. You test, and then you retest to see, do the same results come out when you do the retest, right, the second test. It's looking for the consistency of scores over time. Now, how much time needs to pass? Depends on what you're looking at, right? Depends on what you're interested in. Sometimes we're just looking at matters of hours or days. Sometimes we're looking at test, retest over matters of weeks or months or years. It's really up to you what you're thinking about in terms of this test retest. I've seen people who do a questionnaire, then they replicate it again maybe a week later just to show that there is some test retest reliability. But sometimes you look at this with over a period of months or like I said, even years. So the test retest reliability in terms of that time frame, that can vary, but the idea is the same, is that we're looking for the consistency of scores over time. Now, obviously, for this to work, you need to be looking at some kind of construct that is relatively stable over time. It won't make sense to look at test-retest reliability of your mood because your mood changes throughout the day. So it really probably wouldn't get the same results. If I test you for your mood in the afternoon, I would expect very different results maybe in the evening or a day later or several days later because our moods are quite variable. Right? So mood is perhaps not something that you would really be looking at test-retest reliability for, but your personality is pretty stable. right? Our personalities are formed when we are children, and those remain relatively stable throughout our life. So we could look at test-retest reliability for somebody's personality, and we would expect to get roughly the same outcomes from when somebody, takes this questionnaire year one, and then they take the questionnaire a year later, right? Because your personality shouldn't change all that much. So you need to think about, is the construct I'm measuring something that is stable? Now, usually we refer to test-retest reliability for the same individuals, but of course it can be used for different individuals as long as they are within the same population. So maybe you're looking at people's overall happiness, and maybe you look at a different sample, but again, importantly, the exact same population, and you might expect to see the same kind of general distribution of overall happiness within this particular population. But oftentimes we are looking at the same individuals. When we think about test-retest, we're usually looking at individuals at time 1, same individual being tested at time 2. Sometimes you will see test-retest reliability being used to refer to two different individuals making judgments about the same person. So what I mean by this is that oftentimes you have kids who give some kind of score about themselves, their own well-being, right? Their own sense of self, whatever it might be. And then you might have parents rating their children's well-being. So you have both the child rating themselves and the parent rating the child's well-being. Both of them are making assessments about the child's well-being. And this is also occasionally referred to as test-retest reliability. Okay, any questions about this one? The second type of reliability, one that's perhaps pertinent to you guys as students, is equivalent forms or alternate forms. And this just means that we might give out the same questionnaire, the same test, but they're different in some ways. Maybe we've changed the order of the questions. Maybe there are slightly different questions. We are concerned, for example, of cheating, and so maybe we have a test bank and we have, every student gets a random 10 questions from this test bank of 100 questions. We want to make sure that the 10 questions that have been randomly selected for you are going to be of comparable difficulty to the 10 random questions that have been selected for your classmate. So we might do an equivalent forms check to see, are the tests that have slightly different questions still equivalent in terms of their difficulty, their length, the types of topics that they're covering, all these other things. We want to make sure that these two forms are equivalent. And this is something that you see a lot in education, where you have maybe version A, version B. But that's it. It's just looking at two different versions, or 3 or 4, whatever it is, and just making sure that they are equivalent. Now you can also think, if you remember last week, we talked about the problem of testing and how sometimes or instrumentation, how sometimes the instrument might change. So you might want to check that if an instrument has changed from year 1 to year 2, that these are still equivalent. Okay, third type of reliability to be concerned about is inter-rater reliability. This is assessing whether we have consistency of scores between raters or between observers. So a lot of research is looking at people making observations about some other individuals. So we have maybe multiple research assistants, and they're all observing a bunch of kids to see, are these kids acting aggressively, for example. Now, aggressive can be a little bit difficult to maybe define, right? Especially if kids are play fighting, it's a little bit hard to know at what point is this real fighting, at what point is this just playing around. So at what point do we call this aggression versus just playing? So you might have some degree of subjectivity between these two events. And so we want to make sure that our raters are consistent in how they're applying this particular scoring index. You guys, again, remember from last week, we talked about problems of validity where we might have raters who are applying a particular instrument differently, right? They're using the scale differently. They're having like criteria for how to assess things like aggression, and maybe they're doing this a little bit different, and that's not a good thing. So we want to check that they are indeed applying our criteria of what is aggression in a similar manner. So that way our data of what is aggression is consistent between our raters. So it has some reliability. We can trust it. So we would look at inter-rater reliability. Now there's two ways we might calculate inter-rater reliability depending on what type of data we're looking at. If we have a continuous scale, so you can think of like judges who are rating gymnasts or rating dives or whatever it might be. You can think of people who are counting the number of aggressive acts that they see. So any kind of continuous variable. And when you have two or more raters, then you might conduct an intra-class correlation. So this is just a way of assessing that the raters are behaving similarly, that they are in fact making similar judgments of how many acts of aggression occurred, or they're similarly judging this number of gymnasts. Okay, it's pretty simple to do on SPSS. Here, I have 10 observations. This might be 10 different kids that these 3 raters observed, right? Or it's 10 gymnasts that we have 3 judges for, or it's 10 movies and 3 judges are rating how depressing they are, whatever it might be. So we've got 10 observations, and we've got 3 people making judgments about these observations. So observer 1 scores across the 10, observer 2 scores across the 10 observations, and observer 3 scores across the 10 observations. How similar are our observers for each one of these observations? That's what we want to know. So we're going to go down to scale and reliability analyses. Now I know it's a little bit small here, but you guys have the PDF, so you should be able to see this okay in your PDFs. So go to scale and go to reliability analysis. Put in your 3 observers into the items here. So you're going to click for a bunch of different information. We want to get descriptives for the items and scales and the scale of item deleted. It's great to get the correlations, get some summary statistics. That's great as well. And then importantly, we want to get the intra-class correlation coefficient. So do make sure that you tick this box down here. Now it gives you a few different options. Just choose two-way mix. There are a couple of other options, but always just choose two-way mix. This tells SPSS that the raters are a fixed variable. It's the same raters that are being used. It's the same 3 raters across all 10 observations. Also ask for absolute agreement. You can either choose linear or absolute agreement, but you want to choose you want to choose absolute agreement because you want to know what is the agreement between your 3 observers. Okay, so for simplicity, just use these 2 options here always. Okay, yeah, like I said, there's a few different options you can do here. Just use two-way mix here. Okay. So this is the output you're going to get. This tells you just what happens. So we have 10 observations here. And we can ignore this part. It gives us a few tables that we don't really need. So we can just ignore this one here. This tells you the summary statistics for each of your observers. So observer 1, across the 10, this person's average was 4.6. For observer 2, they had a slightly higher average, 6.7, and observer 3 was in the middle, 5.5. So this tells you roughly how each observer was behaving. This can be helpful because maybe you have someone who is like really, really high or really, really low, from the others. That already tells you, hey, someone's maybe misusing the scale. They're way off from the others. So this already kind of gives you a sense for how similar are your observers. This is the correlation between your observers. So to what extent is observer 1 correlated with observer 2 and observer 3? So you can see that observer 1 and observer 3 are more strongly correlated compared to observer 1 and observer 2. Again, this might be just kind of useful, just gives you a sense for what's going on with your observers. And then this is the average across all 3 of your observers. So across all 3, the average rating was a 5.6 across all 10 of those observations. Okay, let's skip down to the more important stuff here. We can again ignore this table up here. We don't really need these 2 tables. This is the main result that we're looking at. So this tells you how consistent are your observers. Are your observers showing a reliable amount of consistency? We're looking for, we can ignore the top line. Single measures is like assuming you have an ideal observer. That's not what we're interested in. What we're interested in is how similar are our 3 observers across these 10 observations. Are they giving similar scores? So go for the average measures down here. This tells us that we have an intra-class correlation coefficient of 0.784. That's pretty good. It's above 0.7, which is kind of the minimum that we want to see. So this tells us that we have a reasonably high amount of consistency between our observers. And importantly, that significance is less than 0.05, which tells us that this agreement is likely to be replicated. So if we go out and we find 10 new observations, we should see agreement again between our 3 observers with 10 new people that they're rating. Right? We should get agreement again. So this tells us that yes, we do have a reasonably high inter-rater agreement, and it is reliable. It is statistically significant, which means that it can be replicated. These 3 observers will have similar ratings for 10 new observations, and yet another 10 observations, another 10, right? We're going to get consistent ratings between our 3 observers, which tells us that they're behaving roughly the same, and that's a good thing. Okay, any questions? Okay, so the intra-class correlation is used when we have a continuous variable, when we're using a continuous measure. How many aggressive acts were being displayed, right? But what if we have a categorical measure? Maybe we have different clinical psychologists and they're trying to decide if somebody has a diagnosis of PTSD or not. So we have a bunch of clinical psychologists looking through a bunch of case studies and they're saying, yes, PTSD, no, this person does not have PTSD. So that's a categorical outcome, right? That's quite different from the continuous. So for this type of outcome, we would use a Cohen's kappa. This is a way of determining inter-rater agreement for a categorical outcome. Now, this is only for 2 raters. There is a similar version if you have more than 2 raters. I'm not going to go into that, but you can, if you want to know more, you can just ask a question on the discussion forum. I can direct you to the information. But this is for categorical data, so nominal or ordinal data. The data need to be paired observations, so each rater is making observations about the same observations, right? So you have 2 raters making observations about, making judgments about all of the same observations. So we have 10 case studies. Both raters are rating those same 10 case studies. So they're using the same scale. That should be important as well. And of course, they're making the ratings independent of each other. Now, of course, this is also true of the inter-class correlation. Your judges or your observers should be making their ratings independent of each other. That's an important part for this to work. Okay, so the Cohen's kappa is used when you have a categorical outcome. All right, so here we have 2 raters and we have a bunch of observations. So this is maybe, yes, there was aggression being shown by the child. No, there was no aggression being shown by the child. Or yes, this person has PTSD. 1 is no, the person has no PTSD, something like that. So we have a categorical outcome, 2 raters making observations about all of this, making judgments about all of the same observations. Okay, so to run a Cohen's kappa, go to your descriptive statistics and then go to crosstabs. Then you want to put in your 2 raters. It doesn't matter who's in the rows, who's in the columns, so just that can be whatever your choice is. Under the statistics options box, make sure to tick the box for kappa. And then under the cells, you want to get the observed counts. So those are the 2 things that are really important here. All right, so this is the output that you'll get, and this is what you want to see. So this tells us that our 2 raters agreed on these 16 observations. So there are 6 observations in which both raters agreed were a 1. So that's aggressive. So we say that 1 is equal to aggressive, and 2 is not aggressive. So both of our raters agreed that these 6 observations, these 6 kids, were indeed showing aggression. Both of our raters agreed that these 10 observations, down that lower left quadrant, are showing no aggression. It's a 2 for both of our raters. Yes? Now we have disagreement between our raters on these 4 observations. Here are 2 observations that rater number 1 said was not aggressive, but rater number 2 said was aggressive. And here we have 2 observations that rater number 1 said was aggressive, but rater number 2 said was not aggressive. Okay? Now, I'm just making this a binary yes-no kind of outcome. You could do the same thing with if you had a category outcome with 3, 4, 5 categories. This is just for any number of categories, but it has to be a categorical outcome. So we have some agreement, some disagreement. Is the agreement between our observers reliable? If we give them 20 new cases, will we get a reliable agreement between them? Even if it's not perfect, will it be reliable? Let's look at the strength of agreement. So we have an agreement of 0.583, that's the Cohen's kappa value, and it is statistically significant. So yeah, there is a reliable amount of agreement. In other words, if we give our raters another 20 cases, they should be able to get a reliable agreement. There should be some consistency in their ratings of these 20 cases. Now, the Cohen's kappa is good, but not great. 0.583, if we were to use these measures here, is okay. It's moderate to good. So it could be better, could certainly be worse. Okay? All right, any questions about the inter-rater reliability? So again, inter-rater reliability is just looking at the consistency between your raters or between your observers. This is something that you would probably be looking at for a lot of research, because a lot of research in psychology does involve multiple raters, multiple observers of subjective things like, are kids showing aggression? Does this person have this particular disorder or not? And so there's a lot of things that we do in psychology that are subjective, and we need to check that our raters are indeed showing some kind of agreement. And it's really important that you do this. You don't want to have one person doing all of the ratings and that's it. Because what if they're, what if the way in which they're using the instrument changes over time? There's some kind of response drift or a rating shift. What if they just weren't paying attention and they missed seeing the kid, punch the other kid? What if they, we're just being really biased in how they're judging these particular observations? So you definitely want to have at least 2 raters, and it's good to have a third rater So that way, when you have this disagreement between your two raters, you have a third one to help settle the disagreement. When you read articles, that do require inter-rater agreement, you oftentimes read that they had, two raters or three raters. Any points of disagreement were resolved through discussion, and they brought in a third mediator to, maybe make the judgment as well. So you'll see papers, where they literally talk about how they're resolving these disagreements and how they approach this idea of inter-rater, inter-observer reliability. So it is a really important part of doing research in psychology. Okay, so our fourth type of reliability is called internal reliability. Internal reliability is really about the internal structure of a questionnaire. And it's asking whether there is consistency between the questions on your questionnaire, between what they call the items on your questionnaire. Oftentimes you'll also see these referred to as the variables. So the questions on a questionnaire are referred to as questions, items, or variables. They all mean the same thing. And we want to check that the items within my questionnaire are relatively consistent with each other, that they're all kind of measuring the same things. We don't want to have questions that are measuring oddball stuff that, that's just quite confusing. It invalidates the questionnaire. So we want to make sure that our questionnaire is looking at the same construct, and all the items within that questionnaire are looking at the same construct. Again, thinking back to last week when we talked about validity, this makes sense. We don't want to have questions about anxiety when we're really looking at depression, right? So we want to make sure that they're all looking at the same kind of construct. So there's a couple ways in which we might check that we have reliability or consistency between the items of my questionnaire. We could do a very easy split half. We take all those items and we literally just split the questions in half, and we just correlate the responses in part A to the responses in part B. Okay, fine. We could also do an odd even. Correlate the questions, the odd number questions to the responses on the even number questions. If they're all asking about the same construct, then we should get a pretty, they should be positively correlated. But there's always the possibility, especially if you have a long questionnaire, that is that the items are just ordered in a funny way. And so you get maybe some, if you did an odd even or just a simple part A, part B split half, that you wouldn't really get a good correlation just because the order of the items is just a little bit funny for whatever reason. So we don't normally just do a split half or an odd even. That's not normally what we do. We, in fact, do a Cronbach's alpha, which is the average of all possible split half combinations. So we are actually doing the split halves, but we're doing lots of different versions of split half all at once. So the Cronbach's alpha allows us to assess the consistency of the items within your questionnaire, with the idea that if we are studying something like anxiety, all of the questions should be looking at anxiety. We should be responding relatively similarly. If I have high anxiety, then I would respond relatively similarly to all these items that are looking at anxiety. Right? If I have very low anxiety, then my responses should also be relatively consistent. I shouldn't be really high on anxiety on one question and really low on anxiety on another question. Right? So we should have some consistency in our responses if all of these questions are in fact looking at the same construct. Now, you run the Cronbach's alpha on all of the items within this scale, but if your scale has subscales, if it is in fact looking at multiple constructs, like the DAS, Depression, Anxiety, Stress Scale, right, then you would run the Cronbach's alpha on each subscale. You don't run it on the full scale. If you're doing, for example, the 5-factor personality, you might run it on each of those 5 subscales, one for each of those 5 personality factors. Why? because the Chromebox Alpha is assessing the consistency of the items that they're all similar. It doesn't make sense that you would run this across both the depression, anxiety, and stress scale because we would expect you to respond different to each of these different constructs. So that doesn't make sense. So run the Chromebox Alpha on each subscale. If you have a questionnaire that has only one construct being measured, then fine, run it on all of the items within that scale. But if you're looking at multiple constructs or multiple dimensions of this construct, then run it on just the items for that particular factor or that particular dimension. Okay, now you should only use this for a continuous scale. That being said, a lot of things that we do are ordinal in nature. We oftentimes use a Likert scale, and people will use a Chromebox Alpha on a Likert scale. So technically it's for continuous variables, but we generally will use it also on these kinds of more ordinal scales as well. You should use at least a 5-point scale or more. If it's 3 points, that's really not going to give you reliable results. So the Chromebox Alpha is going to give you a score between 0 and 1. 1 indicates perfect consistency, perfect reliability. 0 means very, very bad, like no reliability. They're all very different, right? 0 is bad. You don't want that. Closer to 1 is good. 0.6 is kind of considered the bare minimum that you should have as to be considered reliable. 0.7 or more is generally better. The closer you get to 1, of course, the better it is. And the nice thing about the Chromebox Alpha is that not only does it tell you whether there is consistency of the items within the questionnaire, it will help you spot out and pick out the ones that are not consistent. So if you have an item in your questionnaire that is different from the others, that is perhaps bringing down your consistency score, it's going to help you to identify it's this item. This is the problem child. Go back and take a look at this particular item here. All right, so let's see, how does this work? Okay, go back down to scale and go to back down to reliability analysis. This was the same procedure we did for the Cohen's-Kappa. Put all of the items of your scale or subscale into the items box. Then tick the box for the descriptives. You definitely want to get scale if item deleted. It's helpful to get the correlations as well. Okay, so here's your output. First thing to look at is, what is the Chromebox Alpha? Is it above 0.7? It is, so that's good. This is telling us that we have pretty good reliability. We have pretty good consistency between the items of our questionnaire. All right, now it gives us two versions of the Chromebox Alpha. Chromebox Alpha or Chromebox Alpha based on standardized items. You guys should know that these are basically the same thing, right? It's just looking at one version, they have taken the responses and standardized them, right? They put them on a normal distribution, or you're just looking at the raw scores. So these will give you the same outcome, right? Even though the numbers vary, they'll give you the same basic outcome. It would be weird for you to get a very low score on one and a high score on another. That doesn't make sense. So usually you don't see people reporting the Chromebox Alpha based on standardized items. Usually people only report the raw Chromebox Alpha. But you have these two options, right? And again, it just means that you can look at these standardized versions if you wanted to. If you, for whatever reason, have items with different response scales within the same questionnaire, then it might be useful to look at the Chromebox Alpha based on standardized items. That's not normal. It's really unusual to have a questionnaire where the response scale differs between items of the same construct. But if for some weird reason you did, then you might want to use the standardized items, Chromebox Alpha. Okay, The correlation matrix is helpful. It can, if you have problems of reliability, you might check here to see, hey, is there one item that has a low correlation with the others? And if you have one item that's negatively correlated, that might be an indication that you forgot to, reverse code something. It's not guaranteed that that's the issue, but it's always good. You guys learned the past weeks that it's good to have reverse worded items. So, I like ice cream, and then later you have I don't like ice cream. And it's sometimes easy to forget to reverse code these items, and if you don't reverse code them, then they're going to come up as being really inconsistent with the other items in your questionnaire. So if you see an item that has a negative correlation with the others, that might be like, oh, yeah, I forgot to reverse code this. So go back, reverse code it, then rerun it again, right? Maybe that might solve your problem. But it's good to look at the inter-item correlations just because that can help you to maybe spot some of those problems, as well as it starts to give you some indication for any items that might be those problem children. All right, now we look down to the item total statistics. This is telling you what happens to your scale if you're to delete any one of these items. So I didn't post the scale descriptors right now, and quite frankly, the average response on the overall scale is usually not that useful. But so knowing how the mean or the variance changes oftentimes isn't so useful if you delete an item. But what is important is this final column. How does the Chromebox alpha change if you delete any one item? Does it go up? Does it go down? If you to delete item number 1, and you only have the 4 items in this Chromebox alpha, this would cause the Chromebox alpha to go from 0.871 down to 0.848. Now guys, do we want it to be higher or lower? What's better? Higher, right? So this is telling us that we don't want to delete item number 1. This is actually going to reduce our reliability. Same goes for item number 2, 3, 4, and 5. So this is telling us that we have a pretty good scale. The items are relatively consistent with each other, and deleting any one of these items would in fact reduce the reliability of our scale, so we don't want to do that. But sometimes you might have an issue where you have a low Chromebox alpha, and you see, oh, if you delete item number 2, this will cause the Chromebox alpha to go up a lot. And that's an indication that, hey, this item is problematic, that this one is not like the others, and it's bringing down your Chromebox alpha score. So then you have to go back to this particular item and to see what's happening here. Maybe if you're only putting in the items from a subscale, maybe you accidentally grabbed an item from a different subscale. Great, that's an easy fix. Maybe it's just a very poorly worded question that was confusing your participants and they didn't know how to respond to it. Okay, so maybe you need to delete it. Maybe it is, I don't know, just a question that, who knows, for some reason it's just not good, right? So then you have to decide, okay, what do I do? Do I delete this question and do I keep it in? It kind of depends on what the question is and what your goals are. If you are trying to create a questionnaire from scratch and you want to make this the most reliable questionnaire, you probably should delete those questions or go back and revise it and then try to revalidate your questionnaire again. Sometimes people keep these questions in even though they have a lower Chromebox alpha because they think it's just really important, right? So there's not one right answer. If you have a question that if you delete it, it causes the Chromebox alpha to change a lot and go up a lot, probably it's a good idea to delete that question. If it only goes up by a small amount, then it's a little bit harder of a call. That's a hard one. You have to talk with other people to decide what you should do in that case. Okay, any questions? Yes. Good question. Are there any ethical issues about removing items from a questionnaire? No, not really. As long as you're transparent about it. So So you can use a Chromebox alpha. The Chromebox alpha is used a lot. You see it reported like in everything. It's used a lot in the early stages of developing a questionnaire. And so, quite frankly, it's common to remove items that don't match well with the overall questionnaire because you're developing a questionnaire from scratch. And so then it makes sense. You should remove those items. And you might say, and again, you see this in papers all the time. Here are the 20 items we started off with. We went through all of these different processes. Here's the final 12 that we ended with. So you might still have them and report the items, but then you say, we got rid of these because, they were bringing down the Chromebox alpha because reasons X, Y, Z. So that's one use of this, is the development of a questionnaire. Other people might use a questionnaire that's already been developed and established, and you still see them running a Chromebox alpha. And maybe they'll have a Chromebox alpha that's a little bit lower than the Chromebox alpha that was reported when this questionnaire was first established. And they say, oh, well, we're using a slightly different population. We're administering this to kids in Singapore, whereas this was originally made for kids in the US, right? So, hey, our population is a little bit different. Sometimes they just go with it and they just use it even though it's maybe not the best. Sometimes they will delete questions. They say, well, we had because of a different population and we thought that these questions didn't seem to translate so well, so we removed those questions. So it's not at all an ethical problem, but you have to be really transparent about what you're removing and why you're removing them. Yeah, good. Other questions? Okay, so quick summary. Reliability refers to the consistency of observations, and test-retest reliability is the consistency over time. Inter-rater reliability refers to consistency between observers. Chromebox alpha measures the consistency of items within a questionnaire, and you should aim for an alpha of at least 0.7 or higher. Okay, oftentimes you will see the Chromebox alpha being done, and based on that, then you might do the validity analysis we talked about last week, like that factor analysis we talked about last week. So these are very much being used in tandem with each other. Okay, so then let's move on to part 2 of today's lecture, which is about different ways in which we can establish better validity through control groups and control techniques. Okay, week 1, we talked about why control groups are good, right? They help us to give a basis for a comparison so we can establish that an effect has occurred, right? If we have kids watching TV and we want to know what is the effect of kids watching TV on their development of language, we need to compare it to something, right? So we see that kids watching TV and they have a certain, language development. They learn, they're giving this many words, on average at the age of 3. But what does this mean? Is this a lot of words? Is this not a lot of words? I don't know. And I don't have kids. And so when people tell me about their kids and, oh, he's walking, I'm like, is that good? Is this what age kids normally walk at? I don't know. Is he early? Is he late? I have no idea. So I need some kind of comparison, right? So this is true in research. Compared to what? Kids who don't watch TV, what is their average language development at this age? Or compared to kids who watch a lot more TV, what is their average language development, right? So we need to have control groups to give us some basis for a comparison so we can understand what this value means. Control groups can also help us to rule out those competing alternative explanations. This is what we talked about for the past couple of weeks. We need to get rid of these confounds, and so control groups can help us rule out potential confounds, both actual confounds of, maybe we have all of the people who are experienced drivers in one group and no experienced drivers in another group. That's not good. Or theoretical explanations that we want to rule out as well. So control groups are really important. There's different types of control groups that you can think of for your experiments. So the standard is the no treatment or the weightless control group. This is one that everybody kind of thinks about. That's fine. And sometimes we just want to establish that an effect has occurred when we do something versus when we don't do something. So giving people this particular therapy means that we have less depression compared to when they don't have therapy at all. when they have not been seen by any kind of therapist, they get nothing. That's okay. Especially if we're looking at something that is fairly new and very, let's say, exploratory, this is fine for a control group. But you're setting the bar really low. Compared to nothing, does anything have an effect? I mean, that's a pretty low bar to clear, right? So although the no treatment waitlist control group is useful, it's a really low bar, and you could do better. And I think a lot of clinical research, should be doing better than that. What's better? Having some kind of active control group, a group that receives something that is comparable to your experimental group, right? So they have the same amount of attention. They have the same exposure to novelty. They have the same, maybe some placebo control, treatment as usual, something where it's not just nothing, right? So if you were looking at the effect of this new journaling therapy, you might compare it to people who are receiving standard CBT. That's a very established, validated form of therapy. Does journaling give you at least as good of therapeutic outcomes, or even better compared to CBT? Don't compare it to nothing, because again, that's really not that helpful, right? If it's giving you significantly lower benefits than CBT, then you don't want to use journaling when you could just be using CBT. So if there's already a good treatment out there, compare it to that, right? It's also good for, like, if you're looking at journaling, people who are maybe having coming in each week, or maybe we'll use hypnosis. They're coming in each week. It's not just the hypnosis that they're getting, but they're getting the attention from the therapist, right? Where I feel important because this is a person who is listening to me, who is engaging with me, who's asking questions. And it's not just the therapeutic, aspects of the treatment that I'm receiving. I'm receiving a therapeutic alliance with this person. And there's a lot of research to show, as we talked about last week, that the therapeutic alliance can also result in benefits by itself. Doesn't matter what the therapy is. If you just go and talk to somebody, that's helpful. That's why sometimes it's helpful just to talk to your friend, even though they're not a therapist, because it's just helpful to talk to people, right? So if you want to establish what is the benefit of hypnosis, you want to compare it to a group who is getting similar treatment with a therapist, who is getting that similar therapeutic alliance and attention, right? So again, don't use nothing as your baseline. Use an active control, somebody where you can control for the overall attention that is being given to this person, the overall therapeutic alliance that's being given. So we want to control for those particular confounds. All right, so it's good to have control groups, whether those control groups are a waitlist, no treatment control group, or better yet, an active control group. It's good to have a control group. How do we decide who belongs to our experimental group and who belongs to the control group? And I'm using this as a binary experimental or control group. Obviously, we might have multiple experimental or multiple control groups. So do be mindful that this can be actually just lots of groups in one study. So how you decide who gets to be in any group, there's a couple ways you can determine this. One is through randomization. Close your eyes. This person goes into the experimental group. This person goes into the control group. These people go to the experimental group. These people go to the control group. You're just completely blind and assigning at random. That could work. And we've talked before about how randomization can be very useful, right? If you have a large sample, randomization is going to help even out those individual differences between your groups, right? Yeah, one person might be a little bit of an oddball, but through a large sample, and just probability alone, you're going to have another oddball who gets in the other group. So overall, it kind of works itself out. That does still require a large sample, and of course, it's not guaranteed that you're going to have equivalence between your groups. So you might want to be a little bit more purposeful in ensuring that your groups are similar to start with. And this means that you're going to match your participants. You're going to match the people in the control group with people in your experimental group on certain demographics or certain scores. So we'll talk about how to do control groups, matching, and then we'll also talk about counterbalancing. Okay, so match groups is when you intentionally create comparable groups on a particular variable that could affect the DV. And it could be variables, right? So you could be match them on multiple, what we call covariates. Now, of course, the more variables you're trying to match on, the more complicated it gets to find a match, right? So if you're wanting to match on age, gender, education, income, and their trait anxiety scores, and their number of traumatic incidents as a child, and like all these other things, it just gets a little bit more complicated, right? But that's fine, you can do it. Match groups means that we are trying to make our groups relatively equal to start with, so that when we do the experiment, any differences we see between the groups at the end presumably can be narrowed down to the manipulation that we administered and not something else, because we've made the groups similar to start with. So how does matching work? You have a bunch of people, you randomly divide them into you match them up. So you match people based on their scores on whatever covariate it is that you're interested in. And then you randomly assign individuals of those pairs to your experimental or your control group. Now, for matching to work, you need to ensure that they are relatively similar on whatever variables you are matching them on. And again, this can be quite complicated if you're using lots of variables to match your groups. It does require a pretest. So this is a little bit more complicated to carry out. If you're just doing randomization, it's easy. The first person who comes in, they get put into group 1. The second person who comes in, they get assigned to group 2. Third person gets assigned to group 3. Fourth person goes back to group 1. Fifth person goes to group 2. Sixth person group 3, so on and so on. That's very easy. If you're doing matched groups, you have to gather your full sample first, administer a bunch of tests to get all of this information for the matching, match the groups, assign them, and then you do your experiment. So you need to have information to start with before you can run your experiment. So it's just a little bit more logistically complicated to carry out because you do have to have this information before you can actually start your experiment. It might also mean that you are going to eliminate some participants from your data because they just don't have an equivalent, right? So if you've got somebody who is really, really high on trait anxiety and nobody else has a similarly high score of trait anxiety, then this person just might be deleted from your data. They just never get included at all because they don't have an equivalent pair. So it might mean that you are reducing your potential sample, or you have to go out and recruit a whole lot more in order to create these matched pairs here. Okay, any questions so far? So matched pairs matching a process is very useful if you want to make sure that your groups are for sure equal on these particular extraneous variables to start with. It's just a little bit more complicated to do. Okay. All right, so now let's talk a little bit about counterbalancing. Counterbalancing is a technique that is employed a lot in lots of different types of research in psychology for ensuring that there is equivalence between our stimuli and between our procedures. Okay, we want to, again, when we think about looking at experimental versus control groups, when we are doing an experiment, we want to make sure that our experimental and our control groups are as similar as possible in all ways except for our experimental manipulation. We want to rule out all of these various compounds that can explain the results, such as the groups being different. Or maybe we want to rule out that we see high responding on Guys, can we try to keep the chatter low so everyone can listen? We want to rule out that there's potential carryover effects. We learned last week about carryover effects, how maybe drinking caffeine in phase 1 could influence responding in phase 2 when you're supposed to be drinking water. Or running, clockwise around a track, right, results in you being more tired compared to when you run counterclockwise the second time around. So we want to reduce the potential for these kinds of carryover effects that might influence responding. So how can we do this? We counterbalance the order of treatments. Okay, so I have a little activity for you guys. Raise your hand when you see the green circle. Keep your hand down when you see the red circle. Okay? Okay. Easy. What does this remind you of? Yeah, traffic lights, right? Red circles are like the stoplight. Green circles are like the go, 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 right? So try this again. Raise your hand when you see the red circle. Keep your hand down when you see the green circle. Okay? All right, good. So it's a little bit harder. There were a couple people who are like, when they say the green, like, oh, no, okay, no, keeping it down. It's an easy task. It's pretty easy to do. But even if it's easy, you're still like, when you see the green circle, you want to raise your hand because we're just so inclined to believe that green means go, red means stop, right? It's a little bit of hesitation. When you see the red circle, it's a hesitation, oh, hand up, right? Because it's just not what you're naturally thinking of when you see red circles. You normally think, stop, don't move. That's what we're taught from a very, very young age. So if you were, and you shouldn't be using red and green circles, but if you were using red and green circles as your stimuli for go, no-go tasks, you should absolutely counterbalance them. Because if the green circle is always your signal for go, and the red signal is always the signal for no-go, it's really hard to know whether people are responding because they have learned this in your experiment or because it just corresponds to what people have learned from outside of the experiment, from just their own life history. If we want to know that people have learned the task in our experiment and that what we're teaching them is affecting their behavior so we can measure the influence of our manipulation, maybe we're looking at memory load or something like that. So how does having some kind of cognitive load influence your ability to establish this go, no-go task? We want to see that the cognitive load really does reduce your ability to process this information regardless of what the color of the circle is. Guys, do we have questions? Okay. So when you have stimuli, like the color of circles, maybe you have stimuli that increase in size. We've seen, in my kind of research, we do this a lot, where you have a particular geometric figure like a triangle is the cue for make a response. And then we want to see how to respond when we make the triangle bigger or the triangle smaller. So sometimes we start off with the small triangle as being the one to respond to and the big triangle is the one not to respond to. Other times it's flipped. The big triangle is the one to respond to, the small one is the one to not respond to. And if you don't counterbalance that, it's easy to make a response to the big one and not to the small one, just because we have certain kinds of ideas about how size and what that means to, go, no go. So anything like this, you want to counterbalance so that you know the behavior you observe in your experiment is due to the training you have given the participants and not due to specific features of the stimulus itself. All right, does this make sense? Any questions? I think another example that might be more relatable is if you're doing a memory task and you have word pairs. So you have two lists, right? List A, list B. So you learn these two and then you give people list A and they have to recall list B. Counterbalance that. For half the participants, give them list A, recall list B. For the other half, give them list B and have them recall list A. because maybe for some reason list A is a little bit easier to remember, right? It's just you didn't quite realize that. Or for some reason list B is easier to remember, whatever it might be. So just make sure you're counterbalancing these types of stimuli. Okay. So counterbalancing improves the internal validity by removing those kinds of stimulus-specific effects, and it ensures that the behavior you observe is really just due to the training and not due to specific features of the stimulus itself. Now, this is better than randomization. I could randomly assign the go signal to being any color, and I could have, Qualtrics or whatever experimental program I'm using use random assignment. But just like randomization can result in fact, imbalances with samples, randomization could result in imbalances with my stimuli. So it's better to intentionally and purposefully equate the identities of my stimuli. Just like we might want to intentionally and purposely equate our participant groups, I want to make sure that for half of my participants, the go signal is the red circle and the no-go is the green circle. And for the other half, the go circle is the green circle and the no-go is the red. So I want to make that very intentional. All right, so we've talked about counterbalancing the stimuli that you're using in your experiments. You also want to counterbalance the order of training or the order of testing. So this, of course, relates a lot to what we talked about last week with that testing effect and the carryover effects, where what you do in one phase might influence what you do in a later phase. So, of course, if you can use a between subjects design, that might be better. This helps to eliminate those kinds of potentials. But sometimes we can't do between subjects design. So then you want to make sure that you're going to counterbalance the order of training and the order of testing as best as possible. So let's say we have two groups. Group 1 gets treatment A. This might be the coffee, followed by treatment B, which is the water. Group 2 gets the opposite. Water, followed by coffee. Now, if we see the same effect of the water and the coffee, regardless of the order in which these things were given, then we can be sure that it's in fact the coffee that is driving up whatever behavior it is. Maybe we're looking at some kind of memory task. We can be sure that coffee is what is affecting memory, and not just the fact that it became, we got it first. Or we can say, yeah, water really does not affect memory. And we know this because even when we gave water after the coffee, we still see the same results compared to when water came before the coffee. So it just helps us to be sure that the results of our experiment are really due to the manipulation and not the order in which those manipulations took place. All right, does this make sense? Now, the more treatments you give, the more groups you need to give to equate these things. So this is 3 treatments. So we've got, let's just say, coffee, water, and tea. And we want to equate the order in which you get these 3 different beverages to assess the effect on memory. And we want to make sure that the effect is not due to some kind of carryover effect. This means that we need 6 groups. Now this is 6 groups per experimental group. So let's just say we have one group who is maybe receiving cognitive load and one group who doesn't have a cognitive load. We want to assess the effect of cognitive load when you also have some kind of caffeine, coffee, water, tea. So it's not 6 groups overall. No. We need 12 groups. 6 for the cognitive load group, 6 for the no cognitive load group. So this is 6 subgroups for each experimental group. And if we have 4 things we need to counterbalance, oh my God, it becomes impossible. There's no way we can do this, right? The number of participants you need is just not possible. So we don't do this. Usually when we do counterbalancing, if it's more than 2 things that we need to counterbalance, 3 is maybe possible, but if it's more than 2 orders that we need to counterbalance, what we'll do is called a partial Latin square. This is partial because we only need 4 subgroups. So it's not fully counterbalanced like you just saw, but it's good enough. It's pretty good. The way this works, so we've got treatment order 1, 2, 3, 4. Participant 1 gets treatment A, B, C, D. So this might be, I don't know, water followed by coffee, followed by tea, followed by Coke. That might be the order in which they receive these different beverages. Now, participant 2 gets the order B, C, D, A. So this will be the coffee, followed by the tea, followed by the Coke, followed by the water. Participant 3 gets C, D, A, B. So this is the tea, followed by the Coke, followed by the water, then coffee. I think that's what the order is. And then participant 4 gets D, A, B, C. So it's the Coke, water, coffee, tea. So across our 4 groups, we see that everyone gets, at least one of these 4 gets the water first, the coffee first, the tea first, and the Coke first. Now, the order is always the same. It's always water followed by coffee, followed by tea, whatever. But the order in which you get them, right? So the first one is always going to be different, right, for across our 4 groups. And so this is kind of generally what people would do when they have to counterbalance a lot of stimulus. We use a partial Latin square. It reduces the number of overall groups that we need to still get a good counterbalancing, ensure that the effects we observe at the end really are due to the manipulation that we gave and not due to some kind of treatment order effect. All right, any questions? Okay, so when you guys are doing experiments, when you are designing your own experiments for your projects, as well as if you were to go on and do one for your honors thesis or for a research assistantship or whatever it might be really mindful of what things you might need to counterbalance. This is, I think, a feature of experimental design that oftentimes gets ignored, but it's super important because it can have really big implications on how valid the results are. Because if you haven't counterbalanced these things, then you're leaving open various confounds. That means that the validity of your experiment has then been compromised. Okay, so be mindful about, do I need to counterbalance my stimuli? Do I need to counterbalance the order of training? Or maybe you have multiple tests. A lot of my research has 3 to maybe 2, 3, 4 tests. So I need to counterbalance the order in which you're tested to make sure that the order is not affecting behavior as well. So if you're doing this kind of research, you need to think about how can you counterbalance to rule out any kind of testing or training order as a potential explanation. Okay, quick summary. Additional groups are included to control for confounds or alternate explanations of the results and to provide a baseline of responding to which the experimental group is compared. Assign groups using non-random assignment or matched groups to equate the groups on non-target covariate variables. Counterbalancing can control for confounds and check that the results are due to training, not stimulus-specific or order-specific effects, and use a partial Latin square to reduce the number of groups needed while still maintaining a counterbalanced design. Any questions about today's lecture? Okay, so here's your 5-point summary for the full lecture. The reliability refers to the consistency of observations. You can calculate reliability for lots of different things, just like we can have validity for lots of different aspects of our experiment. So the ICC is when you want to assess inter-rater reliability between raters for a continuous measure. The Cohen's-Kappa is used for categorical. Cronbach's alpha is used to assess internal reliability of a questionnaire, aim for 0.7 or higher. Whoops. Control groups are necessary, and you want to make sure that they're as similar as possible. And then, of course, try to make the designs counterbalanced in order to real alternative explanations. Okay, if you have any questions, read your textbook, the Christensen, Chapter 7, ask questions on the discussion forum. You can always email me for individual consultations. So we'll end with our quiz yourself. So go ahead and go to the Woo Clock. Okay, so, all right, so when should you check for a test-retest reliability? Seeing a pretty good measure. Always, when checking that the tests are roughly similar, measuring feelings of tiredness or measuring life satisfaction here. Okay, so what's the answer? Oops. I don't know why the correct answer is not showing. The correct answer should be when you're measuring life satisfaction. So, test-retest reliability, remember, we use when we are measuring things that are relatively stable over time. That's why we don't use it for measuring tiredness, because tiredness changes a lot, even just throughout the day, right? We have points at which we're tired and points at which we're not tired. It doesn't really make sense to measure test-retest reliability of tiredness. You don't always have to measure test-retest reliability. This is something that it depends on what you're measuring. If we're looking at whether two exams are roughly similar, that would be more like testing for equivalent forms. So we should be looking at when we're measuring something like life satisfaction, this would be a good time to check for test-retest reliability of our questionnaire. All right, next question. Okay. So, guys, sorry, I just realized I made a mistake earlier when I said something. And I talked about this particular kind of example where two people are rating the same behavior. So you have the parent rating the child's behavior and the child rating their own behavior. I think I mentioned that this was an example of test-retest. That's not. It is inter-rater reliability. That was my mistake. Sorry, I mentioned that earlier. That was my bad. It is inter-rater reliability, not test-retest. Okay, so next question. Okay, so, all right. Joe created a questionnaire to measure students' outlooks on the future, and he designed the questionnaire to assess two major ideas, one related to job prospects and one related to environmental issues. He conducted two Chromebox alphas, got a 0.84 for the job prospects and 0.39 for environmental issues. What should he conclude? The correct answer is all items in the job prospect scales are measuring the same construct, but all items in the environmental scale are measuring different constructs. Yes, correct. Number 3 here. So the first scale with a 0.84 has good internal reliability. This suggests that, yes, these items are measuring similar things, versus the 0.39 for the environmental scale that would suggest that those items are measuring different stuff. That's a very low Chromebox alpha. So the correct answer here is C. Okay, you should always use an active control instead of a no treatment waitlist control. Okay, what we have here, false. Yes, that's the correct answer. It's great to use an active control when you can. Sometimes we can't, and sometimes we're looking at something that is just really novel. We just want to establish, is there an effect of this particular manipulation? So while at various times, certainly active controls are going to give you a lot better information, it's not that you always have to use an active control. The no treatment, the waitlist control, can be really useful at times. It depends on what you're looking at. Okay, next question. I think that's it. Okay, all other things being equal, you're more likely to observe a significant difference between matched groups compared to randomized groups. Okay, the answer here actually is true. If you match on everything else, you're reducing the amount of non-systematic variance. So if there is an effect, if one actually does exist, you're more likely to observe it if you are controlling for all of this non-systematic variance. That's why matching the groups can be really great, because you're removing all of this like random noise that might exist. It does help to equate the groups a lot better. Okay, so when should you counterbalance the stimuli shown to participants? Or sorry, why? Okay, so we have to ensure that all participants receive the equal exposure. Participants don't get bored. Test results are due to training, not what they experience with the stimuli. Yes, the correct answer is yes, C. So we want to do this to ensure that the results we observe are due to the training being given and not to any kind of outside experience with the stimuli itself. Good. Okay, I think that's it. Okay, so that's it. Any questions from today's lecture? Okay, then I will see you guys next week. Thank you.